Good morning and welcome to Physics SCIT 1420. This is problem set 3. In just a few minutes, we're breaking down 5 fundamental forces that shape the way the world moves: torque, friction, resolution of forces, centripetal force, and centripetal acceleration. Let's simplify the science. Now, torque. As you can see, torque is rotational force. Think of turning a wrench. The longer the handle, the more torque you apply. And torque is calculated as force multiplied by the distance from the axis, which means more the distance, more the twist, or more the force, more the twist. So if you look at this diagram, you can see that the axis of rotation is right here. This is the axis of rotation. The force is being applied perpendicular to the door. So if you take the perpendicular force and multiply it by the distance, you get the torque. It is that simple. So the most important thing to understand is that when you calculate the torque, the force taken and the distance from the axis of the force, they must be at right angles or they must be perpendicular. So that is torque. Friction. Friction is the invisible force or the invisible grip between surfaces. It always exists. It resists motion. That means it's always against the direction of motion. And friction is the cause why your shoes don't slip on the floor. Now, what happens if there is a little bit of water between the shoe and the floor? Everybody knows that then there's a bigger chance of slipping. And this is because friction has been reduced. So that means friction depends on the nature of the surfaces in contact. There are 2 kinds of friction. Static friction holds objects in place. That means there is no motion between the 2 surfaces. On the other hand, kinetic friction slows them down when moving. So there you have motion and friction is opposing the motion. As you can see in this diagram, if the direction of motion is to the right side, then friction is to the left. So friction always opposes motion. Number 3, resolution of forces. Force is a vector. That means it has a magnitude and direction. Each force can be broken into components: vertical, horizontal, or on the x-axis and the y-axis. The x is the horizontal and the y is the vertical. A simple example is like aiming a slingshot diagonally. Now when you pull, the pull has 2 directions. One is along the x, the other is along the y, and these 2 work together to create the final path. If you look at the diagram, you see the vector A. You can see the vector A, which is the sum of the x component and the y component. So this is the x component and this is the y component, which could also be shown here. So that's where you get that triangle. So when you get the triangle, and if you take this as the angle, the x component is always cosine of the angle and the y is sine of the angle. So for example, if vector A is 5 units and the angle is 20 degrees, then the x component would be 5 cosine 20 and the y component would be 5 sine 20. Centripetal force. This is a force that acts on objects in circular motion, like a planet orbiting the sun. Objects are held in place by the centripetal force. That means they are compelled to move around along that circular path because of the centripetal force. The centripetal force is always directed towards the center, and it's constantly pulling the object into its curve. You can see that the centripetal force F sub c is towards the center, and that is what keeps the object in its circular path. It's important to remember that if the radius is bigger, then the centripetal force becomes smaller. Alright, so a bigger radius, smaller centripetal force. And on the other hand, a smaller radius gives rise to a bigger centripetal force. Finally, centripetal acceleration. Now, when an object moves in a circular path, let's say that its speed stays constant. So this number does not change. So let's say it's moving at 10 meters per second consistently. Now, although the speed is constant, the direction is changing because it's moving in a circular path. That means it has an acceleration. This is called the centripetal acceleration. Centripetal acceleration is due to the change in direction. So a greater speed means stronger acceleration. So those are the concepts for problem set 3. Alright, now let's get on with the problems. This is problem number 1. You can see that two people are sitting on opposite ends of a teeter-totter. If you look carefully, you can see the forces acting. The first force acting vertically down is the weight of the woman, F sub W. Second force is the weight of that unknown object. I mean, we don't know the mass or the weight of the object. That's why there's a question mark there. That's the second force. The third force on the right side is the weight of the man, F sub M. And finally, the only upward force is the force at the support, which is acting up. It's called the reaction, or it's called the normal reaction, because it's perpendicular at the support. So those are the 4 forces. In the first part, you are asked to draw a free body diagram and to include the force from the support. So what I have just mentioned is the free body diagram, where you show all the forces acting. 1, 2, 3, and 4. You have your free body diagram. What I've also done is I've calculated the forces. Now do remember that force is mass times the acceleration due to gravity. So the force of the woman, which is the weight, is the mass, which is 60 kilograms, times 9.8. So the 60 kilograms times 9.8 gives you 588 Newton. That is the first force. The force of this object is its mass, which we do not know, times 9.8. So you have to leave it like that. And then the force due to the man is the weight of the man, which is 80 kilograms times 9.8. So that's the part A. Now part B, calculate the counterclockwise torque for the system. You see that these two forces are trying to rotate it counterclockwise, which is this way, right? This and this are trying to rotate it counterclockwise about the support or about the pivot.
Yeah.
So how do you calculate the torque? Remember, it is force multiplied by the distance. So when you calculate the torque due to this. It has to be this force times this distance. Okay? That's why it's given as force of the woman, which is the weight, which we already calculated. So you put 588 there, multiplied by this distance, which is 1.5. You can see that. That is the counterclockwise torque due to the weight of the woman. But you also have to add the torque due to this mass, which is F sub A times 0.5, which is this. So you'll have to just substitute that there. And you cannot get a number because you do not know exactly how much this is. So just put this as M sub A times 9.8 times 0.5. Hope that makes sense. Now similarly, you have to calculate the clockwise torque for the system. Now, clockwise torques are taken as negative. So that's why whenever you calculate a clockwise torque, put a negative before you do the math.
Yeah.
So this is net torque clockwise is negative because it's clockwise, Fm times this distance, which is 1.25. Okay? So in place of this, you're going to put this number 784 because we already calculated that. And then you would get negative something, which is the answer. Part D, what is the total torque? Now, if a system is stable, such as this, you can see it's balanced, it's stabilized. That means the total torque and the total force both must be zero. So that's why the answer for D is net torque is zero and the net force is also zero. So now what does that mean? It means that if you add the clockwise and the counterclockwise torques, you must get zero because the net torque is zero, right? And so since we have the total counterclockwise torque from here and you have the clockwise torque from here, you just put those two and do the math to solve for the mass of the mystery object. Okay, you have to substitute these numbers from B and C and then solve for the mass of the object. That is question number 1. All right, on to question number 2. All right, so you see the two muscles in the back of the leg pulling upward on the Achilles tendon, as shown in the figure below. These muscles are called the medial and lateral heads. Okay, and what are you supposed to do? Find the total force in the X direction. So this is where we have to resolve the forces. You can see that the force is 200 Newton on both the muscles. It's 200 Newton here. It's also 200 Newton here. So I have shown you how to resolve the force. So here you have the 200 Newton and then you set up a triangle where you have the X component and the Y component, okay? And that could have been drawn here as well as the same triangle which I've drawn on the right side. First of all, since this angle is 20 degrees and you know that the total angle is 90, this should be 90 minus 20, which is 70. That's why I've shown this angle as 70. And so now you know this is 200, okay? This is 200, and this angle is 70, so this must be 200 times cosine 70, and I get it. And then similarly, this is 200 times sine 70, which is 188. Now, why is it sine? Because this is the opposite side. Why is this cosine? Because it's the adjacent side. So that's how you resolve the two You resolve the force into its two components. And since you're asked to find the total force in the x direction, remember that you would do the same thing here. So you would resolve this into its x and y. And if you take a careful look at that, you see that the two x components are exactly equal and opposite. So both of them will be 68.4, but one is positive, the other is negative. That's why the total comes out to be 0. So there is no net force or total force in the x direction. In the B part, you have to find the total force in the y direction. If you look at the y components, you see that both of them are going to be pointing upwards. So you have the y component from here, which is pointing up. You also have the y component of this force, which will also be pointing up. So you have 188 Newton twice. So add them up, you will get the total, right? That should make sense. And then you have to find the net of the two components. So find the magnitude of the total force. This word magnitude means absolute value. So that's written in math like this, absolute value, which means you're not concerned about the direction, positive, negative, you don't care. It's always going to be positive. So what you got to do in this case is, remember, there's no force on the x-axis, and here you got a total force on the y, which means that the answer to part C would simply be what you got for part B. All right, make sense? Because there's nothing on the x-axis. Find the direction of the total force on the tendon. Oh goodness, that's in the y direction because there's nothing on the x direction. So that's question number 2. Let's move on to question number 3. You know, when you feel tired, when you feel sleepy, the first thing that happens is the head tends to move forward to the side. It's very difficult to hold your head upright when you're tired. In this diagram, you have the head held upright and its center of gravity, which is here, is not directly over its major point of support. You see, the point of support is here, but the center of gravity of the head, which means where the weight of the head is acting, you see, look down, you can see the weight of the head is acting through the center of gravity, but the support is here. What does that do? It creates a clockwise torque, does it not? That would be the weight multiplied by this distance. Now, if that's the only torque, then the head is going to go down like that. Now, to keep it from going down, the splenius muscle in the back of the neck must exert a force, as you can see here, which provides the counterclockwise torque. See that? It keeps it that way. And that balances the weight, creating the clockwise torque. How do you calculate this torque? It is simply the force in the muscle multiplied by this distance, which is the counterclockwise torque. Hope that makes sense. Now let's go to the questions. Find the weight of the head. That's easy. The weight is always mass multiplied by acceleration due to gravity. The weight of the head is 5 kilogram, and then you multiply it with 9.8, you get the answer here in newtons. In part B, find the torque due to the weight of the head. I already told you. Whatever is the weight that you get from here, multiply that with D, which is 2.5 centimeters, see? But we can't use centimeters, so you have to change it into meters by dividing by 100, which I've done. And that will give you the torque due to the weight of the head. Next, calculate the force due to the splenius muscles, okay? Now what you have to do is you have to know the force in the muscle, which we do not know, so we will just put it as F sub m times D, which is 0.5, and set it equal to Fg times 0.025. Actually, the answer that you got here. Now, the idea that we're using here is that the counterclockwise torque is exactly equal to the clockwise torque. Or in other words, the net torque is 0, right? Because one is positive, the other negative. Okay, so that's where. So you have this right side is the answer that you got here. And then you can solve for the force in the muscle. And once you get that, find the torque due to the splenius muscles. Okay, that is this thing. Once you got this number in part C, just use that answer to multiply it with D, which is 0.5. You get the torque due to the splenius muscles. And then the simplest question of all, which I've been explaining, is which force makes a counterclockwise, which is clockwise? Well, look at the diagram, and you know this is clockwise, this is counterclockwise. So figure it out, okay? That is question number 3. Brings us to question 4. It's about friction. Question says that friction between tires and pavement supplies the centripetal acceleration necessary for a car to turn. So when a car is taking a turn, the centripetal force is actually provided by friction. And then you have the coefficients of friction for rubber on concrete. You're given 2 values. One is the coefficient of kinetic friction. The other is the coefficient of static friction. And that's when the road is dry, and then you also have it when the road is wet. The mass of the car is 1,000 kilograms. Let's go to the diagram. So the car is taking the curve. It can be any one of these cars. Doesn't matter which way it's going. Whatever way it's going, the centripetal force has to be towards the center of the circle. So on the red car, it will be towards the left. On the white one here, it will be towards the right. Excuse me, which is what I've shown. So that's the centripetal force, which is actually friction. And then the other 2 forces on this car are, one is its weight, okay, shown here, vertically down. And the third force is the reaction on the road. There, that's shown here. Okay, so those are the 3 forces acting. What is the normal force on the car? Normal force is the reaction, which is the weight of the car. It should be the same as the weight of the car, because the car is neither jumping up or being pressed down. You want it to be balanced. So these forces, this is the same as this, and you know this is mg. So since you're given the mass of the car, 1,000 kilogram, just multiply it with the value of g, which you know, and you get it in newtons. The B part, what is the centripetal force on the car? Now centripetal force, remember, is friction in this case. The formula for friction is the coefficient of friction. The road is dry and we don't want it to be slipping, so we use the static friction. Because remember, even though the car is moving along the road, we don't want it to slip across the road. So it's not actually moving in the direction of the centripetal force. You know what I mean? We don't want it to move off the road, do we? We want it to keep moving on the road. We don't want it to go off the road. So that's why we're using static friction, which is 0.7, right? Static friction. when it's dry, the road is dry, here, when the road is dry, static friction is 1.0. So I have used the wrong number. Please use 1.0 here. It should be 1.0. Coefficient of static friction when it is dry is 1.0. So use 1.0 times the normal force which you got from here, okay? And you would get that. Okay, I've changed that now. It's 1.0 times whatever you got here. Part C. Calculate the maximum speed at which a car can turn if the radius is 30 meters when the road is dry. Okay. Now, the formula for centripetal force is mass times velocity square by radius. Okay. Mass times velocity square by radius. So what you do is, since we already know the centripetal force from part B, the answer to this, whatever you get, put it here and set it equal to this mass times velocity square by radius. You know the mass, 1000 kilogram. You're given the radius as 30 meter. Put those two numbers here and solve for the velocity. Alright, so we have to do the same thing when the road is wet. When the road is wet, what is the centripetal force? It's mu k Fn. When the road is wet, what was the value of mu k? Is 0.5. So hopefully I've used the correct number here. Let's see. Where is that? Okay, I did not put the numbers, but you have to use 0.5 times F sub n. Now F sub n is the same as what you got here, okay? 0.5 times. And then just like we did for part C here, calculate the maximum speed. But this time use the answer here and it set it equal to mass times square of the velocity by radius. I hope that makes sense, and solve for velocity, okay? And then that brings us to the last question. Calculate the acceleration of a 0.55 meter diameter car tire while the car is traveling at a constant speed of 25 meters per second. You're given the diameter, half of that will give you the radius, and you're given the velocity, which is called the speed here, same thing. And then all you got to do is use the formula for acceleration. Centripetal acceleration is velocity square by radius. Substitute the numbers and you will get it in meter per second square. Okay. And then you have to do the same thing, because now you're asked to compare this with the acceleration experienced by a jet car tire. Again, its diameter is given, but look at the speed, it's so much higher. So that means you have to use the same formula to calculate the centripetal acceleration of the jet car tire, and you will get another number which will be much bigger because this is big. Do not forget to square it because the velocity has to be squared, okay? Be careful, put that in. So now you have a second answer, and when you're asked to compare, you have to take the ratio. So take the ratio of this answer divided by this, okay? So that's what I've done here. Take the ratio and you will get a very small number. If you want it to be a percentage, multiply that with 100, okay? And you will get it as 100 in percentage. So that is problem set number 3 done. I hope you understand this. I know I have to move fast, but you can always pause, go back and try to understand it. If you did not understand anything, just get back to me and I will support you as much as I can. Thank you, and we'll see you on the next one.